Okay, this is a short tutorial talking about error uncertainty, and so how we propagate error through measurements and through calculations. So in every calculation, or sorry, in every experiment, you're always going to have uncertain values. So you're going to make a measurement, you're going to estimate probably the last number in your measurement is going to be uncertain. And you can estimate that uncertainty in various ways. For the investigations that we're going to work on, we're going to actually just look at how we can do this by just estimating and making an educated guess as to what we think the uncertainty is. But the key for doing this, and the main reason, is that when you state a final value, sure, you can do the significant figures, and that's great. But in real measurements, what you need to look at is how the error propagates through. So it means when you get your final value, what is the plus minus that you're expecting to see based on the measurements that you made? This is crucial in all sciences, whether it's physics, biology, chemistry, whatever. You need to do this. It also works in statistics and in other mathematical fields as well. Now, we won't get into the whole rules, all of the rules behind this. We'll leave that for university. But we have, there's calculators online that you can use that will help you navigate this and sort of do these estimates early on in your high school career, so that you can make measurements and understand the idea of uncertainty and how important it is in measurements. Okay, so let's take a quick example, and you can apply it to your investigations from this point forward. Let's say a physicist measures the initial speed of an object. Here it's 3.5 meters per second. The time it accelerates for 2.0 seconds, and the distance it travels during this acceleration, which is 12.35 meters. Calculate the acceleration and state the uncertainty of that measurement. Well, when the measurement was done, whatever technique the physicist was using, they determined that the speed of the object via ticker tapes, you could use radar gun, you could use ultrasonic rangefinder, anything like this. They found it to be 3.5 meters per second. Now, the measurement tool they were using was only accurate to about 0.2 meters per second. So it means that when they got that value at 3.5, it could have been 3.7, it could have been 3.3, or somewhere in between. So they estimated 3.5, and they said there's an error of plus or minus 0.2 meters per second. The time they measured to be 2.0 seconds plus or minus 0.1 seconds. So the timing apparatus, they assumed or figured out that their error in their calculation of the time was about 0.1 seconds. Again, there's different ways of doing this, and that's for another topic and for another day, but at this point just we're going to follow the procedure through. And the displacement that they found was 12.35 plus or minus 0.05 meters. So they were actually a little more accurate with this measurement. They were into 35 centimeters, but then they were like, it could have been 12 meters and 40 centimeters, or it could have been 12 meters and 30 centimeters. And so they weren't really sure. So the range that they gave it was about 5 centimeter range, or 0.05 meters. How does this affect the calculation? When we get our value for the acceleration, what is the result? Okay. All we do is we take our kinematics equation here. Delta d equals v1 delta t plus a delta t squared over 2. Great. Isolate for a, so we simply subtracted the v1 delta t from the left. We multiplied all of it by 2. We divided by t squared. Very simple. So our result is going to be approximately something, plus or minus something else in meters per second per second. How we're going to handle this is we're going to start our calculation right here. We know that we need to evaluate the numerator first. So we're going to take this v1 delta t and solve that. Well, v1 was 3.5, so we come to our calculator with 3.5. It has an uncertainty of 0.2. Now, dx, or delta x, is our uncertainty, so see how it's put in here, 3.5 plus or minus 0.2. It is a multiplication, so we change the operator to multiplication. The y value is time, which was 2.0. And you must put in 0 first, 0.1, like so. So here's the expression. 3.5 plus or minus 0.2, 0.0, now they just left off the 2, plus or minus 0.1. We need to find that value, so we're going to calculate. The result is 7 and now the error that's propagated, it says that we know that the value v1 delta t, or the distance it traveled in that time, I guess, if you think about it that way, is 7, and we're uncertain to about 0.53, which is different than the 0.2 and the 0.1. Okay, so now what we're able to do is we can actually store this like so, and we are going to use this number, and we're going to take the distance and subtract this result, which was v1 delta t. So I'm going to replace this with the y value. So see how I stored it, I stored it in the memory, and I did a memory recall, and I put it back to the y. You could have just typed it in as well, or copied and pasted it. You could just highlight it and copy and paste it in here, but it's just faster doing that. Now, we know that what we're going to be doing is subtraction, and the x value, the delta d, was 12.35 plus or minus 0.05. Subtract the result of v1 delta t, which is this. You can see here's the expression. Calculate. Now I know the result is 5.35, and the delta dz is, didn't change much in this case, just by a very small amount, because we actually knew the z value quite well. We knew the displacement value quite well, so it didn't affect the error overly. Now, the next part, I'm going to store that. I'm going to use this again as y, and up here we're going to multiply by 2, and it has no error. It's just a number. It's a constant in this equation, so it's known exactly to be 2. So it has no error in x. We're doing multiplication, because I'm taking 2 and multiplying the result. You might want to write this stuff out when you're doing it. Alright, 10.7, and you can see that it actually multiplied this value. It exasperated the error, because this value went up by 2, so did the error value. Okay, store it. Now this is going to be this divided by delta t squared. So I'm going to recall this in x instead this time, because it's the numerator, and I'm going to divide by the time, and the time was 2.0 plus or minus 0.1. Now I can't do the square here, so I am going to, at this point, just hit calculate. So I'm going to divide it once and divide it again, because that's what squaring means. So I'll calculate it. There we go. I will store it again, recall it as x, and I don't have to change anything here because I'm dividing it by that again, because it's delta t squared. Calculate, and we get 2.67 plus or minus 0.3, as you see here. Now our sig figs say that during the multiplication here, we're really only going to one decimal place in this case, so we're going to get 2.7 plus or minus 0.3. So the result is that we are pretty, our measurement for acceleration based on this experiment would be 2.7 meters per second plus or minus 0.3 meters per second. So it could have been 3, it could have been 2.4, any range between there. That's how you use the calculator, and that's how you propagate error. If you want to learn the rules, you can leave that for university, but there are links online that you can follow and learn the basic rules for multiplication, addition, subtraction, division, exponents, multiplying by constants, and all that kind of stuff. Okay. Now you can use this in your investigation and any other activity that you do where measurements are recorded.